Alright, hello and welcome everyone to our first topic in the HSC course of Extension 1 Maths. This topic is called Mathematical Induction, and it's a type of proof that we use. So the whole idea, the way the proof works is, and this is why we've sort of got the dominoes going at the moment, is you'll have some sort of statement, and this will make more sense when we actually get to the question. But the idea is you want to prove that a statement is true for all numbers. So what you do is you start off by showing that if it's true for one number, it'll be true for the number after it. And so if you have that situation, this is what we call like the induction. So we're going to show algebraically that if a statement is true for one number, then it must be true for the number after that. And then so if it's true for that number, then it must be true for the number after that. And then the number after that must be true, and then it must be true for the number after that. And through this mechanism, we can show that it's true for all numbers. Now again, this will make more sense once we actually get to a question. But all I want you to do is think of at the moment is the dominoes. You know that if one of those dominoes falls, it will knock over the next domino. So with mathematical induction, what we need to show is if one domino falls, it will in turn knock over the domino after it. If you show that, all you then need to do is show that as long as one domino has fallen, then you've already proved that, well, the next domino will fall, and then the one after that will fall, and then the one after that will fall. So this is kind of like a mathematical proof, synonymous with the dominoes. Anyway, I'm not sure which cat was my favorite. I think it was the one that was licking the bowl. They're all pretty cool. But with that being said, let's just get straight into it. Mathematical induction. I'm going to show you some questions now. Alright, so here we go. So maybe a whole lot of what I've just said hasn't made a whole lot of sense. But let's get in and let's see if we can fix that up. Alright, so I'm just going to show you 4 different questions. The first 3 are examples from the textbook. The 4th question is just a question I grabbed from the exercise. That's a little bit different to the examples. Now, in this first one, we actually have a really interesting proof. Maybe one that is actually true, but maybe you didn't realize. We've got 1 plus 3 plus 5 all the way up to 2n minus 1. And it's going to be equal to n squared. Now, what does this actually mean? Well, pick an odd number. I mean, like any odd number you want. Right? So let's say you pick the number 7. Now, what this proof is saying, or what this theorem is saying, and we're going to be proving that it's actually true, is that if we've got this odd number 7, for example, is that if you add up all the odd numbers up to our chosen odd number, right, if we actually add them up together, what do you end up getting? You end up getting 16, right? I've just added those numbers together. Well, that will actually be the same as just going, hey, n squared. We had, in this case, 4 numbers here. So instead of actually adding up those 4 numbers separately, we could have just went 4 squared, right? 4 fours are 16. Or let's say instead you choose a different odd number. Maybe you choose the odd number 11. Let's start adding up those. Add up all the odd numbers from 11. Right, in this case, what do we end up getting? You know, I'm like 20, 30, 36. Right? Well, instead of actually adding up those individual numbers, we've got this theorem here that says, hey man, like you can add them all up if you want, but it's just going to be equal to, well, check it out. There was 6 numbers. It's just going to be equal to 6 squared. And you might realize, well, what's the whole point of this theorem? Well, in this case, this theorem, although being kind of cool, isn't all that useful unless, for example, maybe you're adding up all of the odd numbers, you know, right up to, let's say, for example, 99. Right, now in this case here, you've got about, you know, what is it, 49, 50 numbers to add up. That's a lot of different numbers to add up, could take quite a while. But instead, of course, using this theorem, we could just go, check it out, n squared, right? That's all we would need to do, and you can just get the answer straight away. So I guess, I'm not sure about the practical applications of it. This topic is really just all about getting you familiar with proofs by mathematical induction. And so I guess that's the main goal, because proving things by mathematical induction is one of the more common types of proofs that you see in mathematics, not just in the high school level, but at the university level. If you're not doing your mathematics, your physics or your engineering, you will actually be doing mathematical induction proofs quite a bit. So so I guess the HSC course is really just an introduction to it for you. All right, so how does it work? So the idea is we want to show that this theorem here is true for all integers, right? They're just your whole numbers. For all integers that are larger than or equal to 1. So it doesn't matter if you choose the number 1, 2, 3, 4, 5. Pick a number. This theorem should work for it. And again, just an example, if you chose, for example, the number 6, right? You write out, what would this theorem look like if you're going up to 6 numbers? I actually think we already did that one. Maybe we'll do the 5. So if we're going up to like 5 numbers, so we're adding up the first 5, odd numbers. And by the way, you might be a little bit confused about what is this 2n minus 1. That's just algebraically how you get an odd number, right? So how I'm getting this, so instead of we already know what odd numbers are, so I just went straight to it, 1 plus 3 plus 5 plus 7, but 2n minus 1 is the way we get an odd number. So for example, instead of just writing a 1 there, I sub the value 1 into 2n minus 1, right? What's 2 lots of 1 take away 1? It gives you 1. And then you move on to the second number in the series. Now we're going to let n equal 2. So it's 2 lots of 2 take away 1, ends up giving you 3. And then, the third number along, you let n equal 3. So you've got 2 lots of 3 take away 1. See, notice how it gives you the odd numbers. So all this theorem is saying, hey, add up all the odd numbers to whichever one you go into. If you add them all together, you will end up just getting n squared. And in the case of 5, you can sub in, all your numbers into that 2n minus 1. But of course, all it's going to give you is, your odd numbers. And if you were to just manually add this up like a sucker, right? Oh, I'm just going to add these 5 numbers together. Yeah, it's cool, and it ends up working, and you end up getting 25. But instead of adding up the individual numbers, right, we could use this theorem, which we're just about to prove, and say, hey, man, it was just going to be equal to 5 squared. And it allows us to find the answer really quickly. All right, so... And again, you'd be wondering, well, that's not particularly useful. Well, maybe not until, you get to a point where they're asking you to add up, 50 numbers, 100 numbers, 120 numbers. Instead of adding up all these separate numbers, instead you could just take one number, square it, and get the same answer straight away. So it's kind of a pretty cool theorem that we're going to prove. All right, so how does it work? All right, so just like the dominoes, you actually need to show that the first domino gets pushed over, right? Or in this case, mathematically, we need to show that the theorem actually works for the very first number, which is the number 1. So what we're going to do is we're going to test the theorem for n equals 1, right? So we're just going to sub in the value 1 and just make sure the theorem actually works for the very first value that we're trying to show. Okay, so left-hand side. So we're going to be adding up all the odd numbers up until, well, in this case, n is equal to 1. So we're only adding up the first odd number. So in this case, the left-hand side is just going to be the value 1. There's actually no adding to do. That's the left-hand side. Now, does the theorem actually work for the value 1? Well, what would the right-hand side be? Well, the theorem says on the right-hand side that that should be equal to 1 squared. 1 squared is 1, and in this case we can see, therefore, the left-hand side is equal to the right-hand side. Thus, the theorem, or statement, or proof, whatever you want to call it, thus the theorem is true for n equals 1. Alright, so we've started off, and this is where we'll always start off our mathematical induction proofs. We need to show it works for the very first value. And in this case, it's 1. Now, the next step is to now assume, so this now comes the actual induction part. The next step is sort of a two-step process. We're going to just assume, just temporarily, that the theorem is true for a particular value. And then under that assumption, if it's true for that value, we're then going to show that it will also be true for the next value along. Right, so our next step, step 2, is to assume the theorem is true for some other value, some generic value, let's just call it k. By the way, I'm using the letter K because like every single textbook I've ever seen has always just used the letter K. Even when I was, at uni, they used K as well. So we're going to assume the theorem is true for n equals K, i.e., what does that mean? It means the first K odd numbers, first, second, the third, right up to, right? So we're going up to the theorem and we're replacing the n with the K, right? So we're going to assume that if you add up the first K odd numbers, it will end up being equal to K squared, right? So that's step 2. So step 1 was just to show the theorem was true for n equals 1. Right, does it actually work when n is equal to the value 1? Yes, it is. Now we're going to say, well, let's just temporarily assume that it's true for when n is equal to k. So that's step 2, right? So this statement right here, we're just going to assume is actually factually true. We will be proving it's going to be true in a moment, but for the moment, we're just going to assume it is. Now we're on to step 3, which is now we're going to consider the next value along, right? So we're assuming that it's true for k. Now we're going to consider, well, what about k plus 1? So in this particular case, when n is equal to k plus 1, so i.e., what is that going to mean for our theorem? It's going to mean the first k plus 1 integers. So there's the first k integers. We're considering the next one along, so we have to add on an additional odd number. So I'm replacing, right, I'm going back to the theorem, and I'm replacing n with now k plus 1. And this here, if the theorem actually works, this here should be equal to k plus 1 squared, right? The theorem says, well, you just take how many odd numbers you have, square it, and that's what the answer will be. Forget all this individual adding. All right, so this is what we need to try and show. And the whole key to it is we have to use our assumption for k, because this whole idea is if it worked for k, right? And again, we haven't tested that it works for k, but let's just pretend it works for k. If this theorem does actually work for k, we need to show that it will definitely work for k plus 1. That's what we need to show. If it worked for k, then it will definitely work for k plus 1, the next number along. This is like the same as the dominoes, right? What we're trying to show is if one domino fell, it'll definitely knock over the next domino. And when we made this assumption here for k, we're not saying a domino has fallen over yet. We're just saying if hypothetically a domino fell, will that domino definitely knock over the next domino in the row? That's what we're trying to show here with mathematics. Okay, so let's consider it. So we're now going to consider when n is equal to k plus 1. So the left-hand side is... All right, all of these odd numbers... This is up to the kth term, but we're going k plus 1, so I need that extra odd number. You know what? I've already written it above. I'm actually just going to simplify it out a little bit. Expand, collect like terms, you get 2k plus 1. So this was the 2 to the k plus 1, take away 1. All right, so this is the left-hand side. We need to show, right, by using that assumption for k, that this here will actually, all of this line here, we need to show that this is just equal to k plus 1 squared. That's what we need to show. All right, so how do we do it? Well, we're going to start by using our assumption. We're assuming, right, that the theorem was true for k. That means 1 plus 3 plus 5, right up to 2k minus 1. We're assuming all of that is just equal to k squared, right? All of this is just equal to k squared. So we're going to come in here and we're going to replace all of this, right? If our theorem was true for k, which we're assuming it is, all of that will actually just be equal to k squared. And that is from using assumption for n equals k. All right, so assuming the theorem worked for k, then that means we're going to end up with this. How can we simplify k squared plus 2k plus 1? It's just a trinomial, factorize it any way you know how. You're not with k plus 1 squared, which funnily enough actually is the right-hand side. We've actually done it. So what we've done is, what we've just done here, we've, forget step 1 just for the moment. Step 1 is crucial, there's marks for it. Just forget that just for the moment. What we have just done is it just assumes, hey, let's just pick some random value k. And let's just pretend, just for the moment, that the theorem actually is true, right? If the theorem was true for k, right, then we've shown here that if it was true for k, when we made this substitution, then it actually also is true for k plus 1. We have just shown mathematically that if the theorem is true for one value, then it will definitely be true for the next value along. That's the hardest part of it, and that's what we've just done. And now our proof is actually almost done, because all we need to do is combine the thing that we've just shown, with the first step. We've shown that the theorem was true for when n equals 1, right? We subbed the value 1 in, and it actually worked. So we've shown that the theorem's true for the value 1, and we've also shown that if it's true for one value, it'll be true for the next value. So if you combine those two ideas, we've got it. So since we know it's true for 1, then we know it's going to be true for the value 2. And if it's true for the value 2, it's then going to be true for the value 3. So on and so forth. And here you have, we've shown that the theorem is true for all integers greater than or equal to 1. Right? Because that process will continue on forever. As long as you got an additional number, we've shown that if it's true for one value, it'll be true for the next value. So then it's true for that, and then it's true for the one after that. And that continues on indefinitely. You've shown that this theorem is true. So to wrap up your proof, all we need to do is just write that all just a little bit nice and neat. So the way we do that is, hang on, so I'm going crazy with colors. So to finish it off, all you would then do is say, hey, the theorem is true for n equals k plus 1 if true for n equals k. Right, that was the induction part when we assumed it was true for k and then showed if that assumption was correct, then it also works for k plus 1. So we've got that. Since theorem is true for n equals 1, therefore, I should say, therefore, by math induction, theorem is true for all, and just sort of repeat what the original question said, for all integers greater than or equal to 1. Okay, so that final statement, it doesn't need to be word for word exactly what I've written here, but it does need to mention that, hey, if it's true for n equals k, it's also true for n equals k plus 1. And you also need to mention, hey, we did show that it worked for the first value to consider. And then by maths induction, it's obviously now true for all values. So this is mathematical induction. If you're freaking out a little bit and it's not making a whole lot of sense, don't sweat. You know, sometimes with mathematics, you just need to see things a few times before it becomes a bit clear. Good news for you is you've got additional times to see it right now. Let's look at our next theorem. This is really cool. It says, hey, pick a value, any value you want, and you just start adding up all the numbers up to that value squared. Well, it's just going to be equal to n outside of n plus 1 times, 2n plus 1 all divided by 6. Seems maybe you're a little bit confused and you're not sure exactly what it means. Well, let's consider it. I mean, pick a value, any value for n, right? And again, we're going to prove that this is true for all positive integers. Again, whole numbers. So I guess when I say pick any value for n, I mean pick any positive whole number you want. Let's say you pick the value 4, right? So what is this theorem actually saying? Well, it's saying if you picked the value 4, then it's saying 1 squared plus 2 squared plus 3 squared plus 4 squared. If you add up all those numbers squared, then you will get a number which is kind of cool. Actually, let's work it out. Was it 1 plus 4 plus 9 plus 16? So you know, was that 30? It's not too bad. You actually end up with the number 30. Well, what they're saying is it doesn't matter what number you chose. In this case, we chose a small number like 4, just because it was easier just to do in our heads. When you add all of these up, the answer you get will actually just be the same as, plug in the value 4 into this expression on the right. That is 4 times 5 times, what is that? 2 lots of 4 plus 1, all over 6. And if you type this into your calculator or do it in your head, it's up to you. I'm sort of thinking let's cancel a little. 2 times 5 is 10. 10 times 3 is 30. If you plug that into, you get the value 30. And say, well, it didn't really save us much time. Maybe it was just better to square and then add the numbers. But, what if you chose the number, 100. Going 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right up to 100 squared. You might be there a very long time, even if you have a calculator, right? But instead of adding up all of those numbers individually, right, we went up to 100. Instead, to get this answer, all we had to do was just plug 100 into this over here. Type that into your answer and you instantly will get the answer to all of that. So again, this is kind of cool. Like, how many times do you end up having to add up, the square of numbers? Not too often. You see it in Pythagoras' theorem, of course, and some other situations, but I'm not saying this is the most useful and this will change your life, but it is kind of a cool shortcut if ever you were in a situation where you did have to do this. But for us, again, don't get too caught up on, when will I need this exact theorem? What we're doing in this topic is we're just practicing how to prove mathematical theorems or statements. If someone says, hey, this is true, right? If you do this, you'll always get this answer. The ability to show mathematically beyond all doubt that that's true, or through going through the proof, realizing that actually it isn't true is quite useful, and something, depending on what areas of future study you go into, you may end up needing. Anyway, let's go ahead into the proof. Okay, so first step, right? We're being told that this thing is true for all positive integers. So let's just start with the very first case, right? This is that first domino. We're going to show right now that the first domino has actually been pushed over, metaphorically speaking. So we're going to test for n is equal to 1, right? So the left-hand side, it just takes whatever value of n you choose, you just add up to that number and make sure you're squaring all of them. Well, the first number, the number we've chosen is 1, so all it is 1 squared, right? There's no extra numbers to add up. All right, so the left-hand side is equal to 1. The right-hand side, what do you end up with? 2 lots of 1 plus, actually you end up with a 3 there. It's all over 6. Hey, you end up getting 1. Therefore, the left-hand side is equal to the right-hand side. And I'll put hence, just for a lol, theorem is true for n equals 1. So we've shown that this theorem actually is true for the very first value. The next step, now that we've shown that it's true, now we're going to do the assumption. We're going to assume the theorem is true for n equals k. So what does that mean? i.e., that will mean that 1 squared plus 2 squared plus 3 squared, right up to k squared. K could be anything, right? I don't know what k is, but we're going to assume this theorem actually is true. And so that means if I was to add all of that together, we would end up just getting, what is the theorem? We're letting n equal k plus 1. What's that? 2k plus 1 all over 6. Okay, so we're now going to assume that the theorem actually does work for this value k, and so this will actually end up being equal to that. I don't know why I'm putting a cloud around this. That's our assumption. Okay, so based on that assumption, now we need to show that if that's true, we need to show that it will work for the next value along. So this is, metaphorically speaking, this is the point where we're proving that if theoretically one domino is pushed over, it will in turn knock over the next one along, right? We're trying to show that this theorem will also be true for n equals k plus 1, the next value after k, i.e. 1 squared plus 2 squared plus 3 squared you know, we're not stopping at k squared. We're actually going right up to k plus 1 squared this time. And it should be equal to, again, we're subbing k plus 1 into our theorem, right? Right here, letting n equals k plus 1. And you're going to end up with like a k plus 1, k plus 2. I'm running out of room. Let me squish a little. It seems terrible, but whatever. Plus k squared plus k plus 1 squared. Okay, and then the theorem will be, it was n plus 1. Okay, I'm letting n equal k plus 1. I'm just going to simplify it here. So right here, I'm letting that n equal k plus 1. So we're going to end up like 2k plus 2 plus the extra 1. 2k plus 3 all over 6. All right, so this is what we need to try and show. Okay, so left-hand side. Right, so start with the left-hand side. That's a squared. All right, that's the left-hand side. We need to show it's equal to that. Well, we've got this cool assumption, right? And you have to use the assumption, right? If you don't use the assumption, then you haven't used mathematical induction at all. We need that whole idea of, we need to show that if it works for this value, then it will work for the other value. If you could do this proof without using the assumption, you wouldn't need mathematical induction at all. You just have a straight proof. All right, so we've got this situation here. We have an assumption for what all of this is equal to. We're going to use that. So this whole thing is going to be equal to, go back to what 1 squared plus 2 squared plus 3 squared right up to k squared is equal to. All of that, all of this is equal to that. Okay, so let's go. Let's replace it. So all of this, right, is just going to be equal to k plus 1, 2k plus 1 all over 6. Because I'm on different pages, I'm going to go back, make sure I didn't make any errors. Okay, that's cool. Okay, and that was by using assumption for n equals k. Okay, so now we've used the assumption. Okay, so this is the whole idea of, okay, so the theorem we're assuming is true for n equals k. Will we end up getting what we need for n equals k plus 1? Will we end up getting this? Well, now it's just an algebra step. I can see we've got both terms. You know what? We need the whole thing over 6. So guess what I'm going to do? Right, times that second term over there, top and bottom by 6. By doing that, it allows us to get the whole thing over 6. And I can see that we've got like a k plus 1 factor in both terms. I'm going to factorize out a k plus 1. Why am I doing that? Because we need a k plus 1 there, right? Right, what are we left over with? From the first term, we're left with a k outside of 2k plus 1. And from the second term, we're left over with a 6 outside of, there'd be one additional k plus 1 term there. Okay, so we have k plus 1. I'm going to expand and collect like terms here. 2k squared plus k plus 6k, that gives us a 7k plus 6. And it's all over 6. From here, we have ourselves, I'm going to go off to the side, we have ourselves a trinomial. That's going to need some factorizing. And we're hoping we're going to get these final two factors here. Let's check it out. So any method you like for factorizing. Let's check it out. What we got 2 and 3 here. Okay, so no matter what method you like to use for factorizing, your non-monic trinomials, you're going to end up with a k plus 2 and a 2k plus 3, which, funnily enough, happen to be the right-hand side. So we've done it. So I actually need to create an extra page here for our final statement, and that is theorem is true for n equals k plus 1 if true for n equals k. That was what we just showed here, right? This whole page here was us showing that if it was true for n equals k, it ended up being true for n equals k plus 1. So theorem is true for n equals k plus 1 if true for n equals k. Since theorem is true for n equals 1, right? Remember right at the start, we showed that it actually is true for the very first one along. And combining these two concepts, it's true for one, and then we've shown that, theoretically, if it's true for any value, it will be true for the next one. So now we have this mathematical induction showing if it's true for one, which we know it is, then it will be true for 2. And then since it's true for 2, it'll now be true for 3, and so on and so forth. And so we have it, and so the final step is, theorem is true for n equals k plus 1 if true for n equals k. Since theorem is true for n equals 1, by math induction, theorem is true for, and again, just sort of copy, right, all positive integers. For all positive integers. And again, feel free for integers to use the official symbol for integers if you wanted. Although technically positive integers is just like the natural numbers. And we're on, who cares? That's it. That is the second proof done. So hopefully it's making a little bit more sense. Let's look at the next one. I'm going to speed it up a little bit because I know I'm taking too long and you're probably bored silly. All right, so third one, we want to prove this statement here. So what is happening? The idea is really simple. Pick any value you like that is a, check it out, positive integer. Wow, what a surprise. They're all like this, by the way. We're proving these things with positive integers. So, choose like 1, 2, 3, 10, 205, 1,024. You pick a whole number that's positive. And what happens is, what this theorem is saying is that number, add that number plus all other numbers up to, so add the number you chose plus all other numbers going up to double that number. If you do that, what does it end up equaling? Bam! That right there. All right, this would be like our shortcut. Instead of actually doing the individual adding, we can just use this shortcut and we get the same answer. So let's just pick a random value. If we're in the classroom, I'd pick someone who loves volunteering information. There's a couple of you, let's be straight up honest. I say, look, give us a number, any number. Maybe don't make it too big because we don't want to be going for too long. And let's say, hypothetically, you chose the number 3, right? So what this theorem is saying is, right, check it out. We're going to let n equal 3. So that means the number that's been chosen, we're going to add up all numbers up to the point where you get to double that number. So I'm going to stop at 6. And you can see why I chose the number 3. Like if you chose the number 12, we'd have to add up all the numbers from 12 right up to 24. Or if you chose the number 30, we'd be adding 30, all the numbers from 30 right up to 60, right? That's what this theorem does. And if you were to do that, you know, what do we end up getting? Like 4 and 10. So we end up getting 18. Well, what we could have done is instead of actually manually adding up these numbers, we could have used this result. 3 lots of the number that was chosen, all times by the number chosen plus 1, all over 2. And if you do that, what do you get? You get like 9 times 4, which is 36, divided by 2. You're not getting 18. Like, you know, that's what it does. And you're like, well, that's not really much of a shortcut. All we had to do was add 4 numbers, but you understand the idea. This theorem will also work if we had chosen number 33. And that would have had us having to add up all the numbers from 33 right up to 66. You see there's a lot of numbers there that you're going to have to add up. And instead of adding up all of those numbers, you could have just instead, you know, just plugged this into your calculator, you know, and like 5 seconds later, you've got your answer. So you can see it truly is a shortcut for any reasonably large number. Anyway, let's go ahead and do, sorry, I said I was going to go quick, and here I'm explaining stuff. All right, let's roll with it. How do we do this proof? So I'm going to start off. Let's show that it actually works for the first value. Tests n equals 1. Left-hand side. Okay, so again, we've chosen as value 1. That means we need to add up all the numbers from the value we've chosen up to double that, right? Which is, so you get to stop at 2. That's kind of cool. You get the value 3. What about the right-hand side? What's happening to the right-hand side? Well, you got 3 times, what have we chosen the value? 1. And then you got 1 plus 1 in that bracket, 2 on the bottom. And you're not getting 3, right? Hey, check it out. Left-hand side was equal to right-hand side. That tells us, therefore, the theorem is true. It worked for n equals 1, right? We've already got it set up. We've shown that that first domino has actually indeed fallen. Now all we need to do is go through the induction part. If it hypothetically falls for one value, will it definitely fall for the value after it? How do we do that? We get into our second step. We assume theorem is true for n equals k, i.e., what are we going to end up with? K plus k plus 1 plus k plus 2 right up to 2k, right? We'd have to go right up to double the number chosen, and that would just be equal to 3k, k plus 1 all over 2. Right, this is our assumption. Okay, so now we're going to consider when n is equal to k plus 1, right? i.e., what are we trying to show? That like k plus 1. So start at the value you've chosen, k plus 2, you know, right up to like, you know, 2k, if I'm to think like where the previous assumption ended. But in actual fact, there'd be extra values. There'd be the 2k plus 1, the next number, and the final number, you know, remember you stop when you get to double the value, which is actually, you know, 2k plus 2, right? And this would be equal to 3. I've squished. That's right. I'll just go to a next line. And so the idea is we're trying to show that this would be equal to, right, the theorem, we're letting n equal k plus 1, 3 outside of k plus 1, k plus 2, yep, all over 2. All right, so left-hand side. All right, buddy. Okay, so I'm just writing out the left-hand side here. There we go, there it is. We're just going to do the same thing we've been doing all along. Okay, we've got this assumption. All right. So our assumption is that all of this is equal to that. Well, we can't just make a straight substitution here because we don't actually have the separate, like we've got all of this part, but we're missing the k. So we could like steal a k from one of these other terms. Or what we could do is we could say, like just take this k across to the other side where it becomes a minus k. You've done a poo. And that's what we're going to do. So we're going to assume that all of this is equal to that. So we're still going to, use our assumption. So this will end up being equal to, what is it? 3k, k plus 1, all over 2 minus the k, plus, and then we've got these final terms here. 2k plus 1 plus 2k plus 2, right? We're trying to show that this is equal to this. All right, so 3k, k plus 1, all over 2. What do we end up with over here? I'm like just collecting like terms here. We end up with 3 lots of k plus 3. Okay, and we want it to look like, right? We want it to look like this. So we can see there's a 3 out the front. The whole thing's over 2. Let's maybe start by just taking the 3 out the front. Right, see, I've factorized out a 3 from the terms. Now we need the whole thing over 2. So what am I going to do? Divide it by 2, times it by 2. So now we've got the 3 out the front. We end up with in here, I could expand it out and then factorize the trinomial, but we already have like a k plus 1 that I can just factorize, leaving us with a k plus 2, and it's all over 2. And again, if you're not sure what I just did then, and if that didn't make sense, you could have just expanded out everything that was inside here. And then factorize it, and you end up, getting the exact same thing. Which actually is the right-hand side. And there you've got your another proof. And then you just finish off the final statement, which is we've shown that it's true for n equals 1. If it's true for n equals 1, like just exactly what we did here. Right, we've done the next one. All right, I've got one final bonus one to do. This one I've just stolen from the textbook because it looks different to the examples officially. So I thought I'll show it to you because you might freak out if you see this one. But it works the same. Again, we're trying to show that this theorem here is true for any value of n. So pick a value of n. Let's say you pick the value n equals 4. Then what this theorem is saying is that a, which is some unknown, plus ar plus ar squared plus ar cubed, right? Notice we go up to the n minus 1th term. So since we've chosen 4, we're going up to 3. Angie, careful with the feet, yeah? Don't touch computer, okay? We're showing that this will in fact be equal to, this. We're going to prove that if you were to theoretically add up these unknown terms, you'd end up getting this. The other reason I actually chose this question is because this is actually a really famous result. You'll see this in the called geometric series. They're super fun. And like I'm saying, they're very well known. There's very well known proof. So I want to make sure you know how to do it. All right, first up, you know what to do. Tests for n is equal to 1. Left-hand side would just be, so in this case, we're letting n equal 1, right? 1 take away 1, 0. So we're going up to the term which is AR to the 0, or in other words, just the very first one, A. The right-hand side would be A. Outside of R to the 1 minus 1, all over R take away 1, they cancel, leaving you with A. Left-hand side equals right-hand side. Therefore, theorem is true for n equals 1. Now we're going to assume the theorem is true for n equals k, i.e. that would be that a plus ar plus ar squared right up to ar to the k minus 1. This will be equal to a outside of r to the k minus 1 all over r minus 1. Right, this is what the theorem would be equal to if it's true for n equals k. So now we're going to consider when n is equal to k plus 1, i.e. a plus ar squared right up to when n is k plus 1, which is going to give you an r to the k. And that should, of course, be equal to, according to the theorem, a outside of r to the k plus 1 minus 1 all over r minus 1. All right, let's check out this left-hand side and see if it actually is the right-hand side. Left-hand side is this. Right, we know, we have an assumption for what all of this is equal to. If this theorem is even true, if it even works, then theoretically all of this should be equal to, according to our assumption, this, right? All of this should be equal to that. So let's make this, let's insert this assumption. And we've got this final term left over on the ends. Okay, so we've got this. Now let's go ahead and, well, let's, again, just algebraically simplify this. We need an r minus 1 on the bottom, right? This is what we're trying to show. So, let's just do the same, times top and bottom by r minus 1. And take this, pull this r, we have this a term, I should say, here and here. Let's factorize that out. So we have a all over r take away 1. And we're left with an r to the k take away 1. And over here, we would have a plus r to the k all times by r take away 1. Okay, so what do we get? R to the k, take away 1, plus r to the k plus 1, right? I've used index law number 1, minus r to the k. And you end up with r to the k plus 1, take away 1, left over, all over r minus 1, which is the right-hand side. Check it out. That's what we wanted to show right up here. And there we have it. And then finish with your conclusionary statement, right? So we've shown that this is true for when n is equal to 1. And then we've also shown that if it's true for n equals k, that's the assumption step, part 2, then it's also true for n equals k plus 1. And that's the induction step. And it's combining step 1, right? Showing that it actually worked for 1, with the induction, that then gives you the proof that it actually works. This result, this original theorem, is actually true for all positive integers. All right, I'm going to leave it there. You have an exercise to do, lots of questions. Surely you will have lots of questions. Some of the questions look a little different to what we've covered, right? They all work the same way. It's the same process, same theory. The algebra, though, you may need some different algebra tricks. If you get stuck on any questions, you know what to do. Either ask a question, leave a question here on YouTube or back through Canvas, and I'll get back to you the best I can. Best of luck, and I'll see you for the next one.